In a 3D space tessellated by cubes, from one point there originates infinite directions, of course. Front, back, left, right, up, down, and many different directions. Some of these directions are, however, special. For example, a direction like this, which is passing through these nearby vertices. Some directions will be like body diagonals of the cube, will be along these body diagonals. So in this sense, we have some very interesting directions which we should be aware of to understand some very interesting properties of cubic lattices. So let's think about one of the octants. So what do I mean by octant? Like in the previous, in this infinite lattice, you can think this is the origin, and this is the, let's say this is the x-axis, this is the y-axis, and this is the z-axis. So from here you can see around this point you have these 8 cubes. First one, second one, third one, fourth one, fifth one, sixth, 7, 8. So these are the 8 octants. So we are looking at these directions in one of these octants. So let's think about one of the octant originating from one of the point, let's say this point. And we need to mark some important points in this octant, these face centers of the unit cell and the body center of the unit cell. And we are focusing on this point. From here, let's think about these directions. So some of these directions are along the edges. Okay, so along the edge we have these many points here. So this is along the edge, this point here is also along the edge. So I will treat any direction along the edge as a similar direction. I know that these are different directions pointing in different pointing towards different points, but they are still, all of these directions are along the edge. So these 3 points will be along the edge, they're gone. How about other points? So some of the points will be along face diagonals. So this point here and this point here is along face diagonal, so they're gone. How many more such points are along the face diagonal? So you can see in the front face here you have these 2 points, they're gone. In the left face you have these 2 points along the face diagonals, so they will be gone. And then we are left with these points in this octant. And then an important direction is along body diagonal. So we have these 2 points along body diagonals, they are gone. How about these 3 points? They are along some pretty interesting kind of a direction, which is not an edge, which is not a face diagonal, which is not a body diagonal. They are some special kind, this is some special kind of a line. So these points are along some special kind of direction. I would like to name this direction as VNFC diagonal. By VNAFC I mean vertex, and NAFC is for non-adjacent face center. As you can see that this line which I have drawn here, this white line, is joining a vertex and a non-adjacent face center, because if you join a vertex and an adjacent face center you will get a face diagonal. So from this point you see that in this cube there are 6 faces. So 3 of the faces, this one, the top face, and the right face, and the back face. This is not on this point, so these faces are not passing through this point, and their face centers are non-adjacent to this point, because the other 3 faces, the bottom face and the front face and the left face, their face centers are very close to this point, and they are along the face diagonal. So this new direction I would like to call it as VNAFC diagonal. So we have these 3 points here along these VNFC diagonal directions. Well, so these directions are very important. This will help us figure out some things about cubic lattices very easily. So now, very interesting, very important thing, like in a cubic lattice, from a vertex, from a particular vertex, how many edges and how many face diagonals and how many body diagonals and how many V and FC diagonals originate. We would like to think about that, not just in a unit cell, in all the 3D space around, So if this is a vertex, in all these directions, which we saw in the first slide, so along all these directions in the infinite space, from a vertex, how many edges will arise? So you can see that you have an edge originating from this point in the upward direction. Similarly, there will be an edge originating in the downward direction, right? The left, right, and then front, back. So if you understand this very interesting geometry here, this geometry, you can understand from here that there are 6 directions in which you will find the edges. So from one vertex there will be originating 6 edges. Okay. Now face diagonals are interesting. To understand about face diagonals, you will have to think like this point here. You can see a face diagonal direction on this face here, but you will have to extend this face where you got this face diagonal, because this is an infinite lattice. So in that infinite lattice, you will see these 4 face diagonals originating on this wall. And then you can think about the other 2 walls. So first this wall, left wall, and on the left wall we have 4 more directions, 4 more face diagonal directions, and on the bottom wall we have 4 more, right? So there will be a total 12 face diagonals originating from a vertex. How about body diagonals? Well, let's change the perspective a little bit to feel the octants, 8 octants. Let's think about this point here in the cubic lattice, and now you can see that from this point there are 8 octants, 1, 2, 3, 4, 5, 6, 7, 8, in whichever order, doesn't matter. So we have these 8 octants, and in all these octants, if we can figure out how many edges, for example, you can see very simply, which we saw in the previous diagram, it's like along these directions. Okay, the face diagonals, 12 face diagonals, you can see here in a better perspective. And then we can think about the body diagonals. Body diagonals, so from this vertex, you can see that in these 8 octants, in one in each octant, you can figure out there is 1 body diagonal in each octant. Okay, so that would be a total 8. Okay, now the interesting part, how many V and FC diagonals? So what were these V and FC diagonals? So let's think about this one of the octant first. In this octant, in this cube, you have 3 non-adjacent face centers, and this, and you can think about these directions. So 3 V and FC diagonal directions in one of the octant, and in the nearby octant again you will get 3, and these lines are not going to coincide with one another. So if you make such V and FC diagonal directions in all these octants, you will get a total of 24 V and FC diagonals, right? So this thing is very important. This whole result is very important. In a cubic lattice, from a vertex, there are these many edge directions, face diagonal directions 12, body diagonal directions 8, V and FC diagonal directions 24. Okay, so whenever you find a nearest neighbor, first nearest neighbor or second nearest neighbor or third one or fourth, whatever, whenever you find the neighbors in the direction of edges, along the edges, you will get a number 6. Whenever you find the neighbors in the face diagonal direction, you will get a number 12. So these are the common numbers which you will see here. For example, coordination number you also see. In simple cubic lattice, the coordination number is 6. In FCC lattice, it's 12, and in BCC, it's 8. Why so? These are these numbers here. Well, 24 is not there because 24 is a little bit of unfortunate kind of a number. It's a very different kind of a direction, but you will see this number also in this discussion. Let's go one by one. Let's think about simple cubic lattice. So you have these points, the center of these spheres or atoms, whatever, at these points. So you have to think about the first nearest neighbor. If you have to think about the first nearest neighbor, let's first choose a point of reference. You can choose any point as your point of reference because this is a lattice, and the neighborhood around any point is different. That is the basic definition of a lattice. So let's choose this point right here and then think about the distances which you get. Okay, this distance here right here is like along the edge distance. Let's say the edge length is a, so at a distance a. This is along one of the face diagonal, and this distance is root 2a. We'll get 12 such directions around this point, right? This is another edge along the edge direction a. This is along a body diagonal, root 3a distance, right? So first nearest neighbor will be definitely along a. You will have to do a little bit of calculation to figure out which distance is longer and shorter, and of course the first nearest neighbor will be along a. So along edges, and the number would be 6. We already have seen this important property in the previous slide, and distance between them is a, right? And you can assume that the nearest neighbors are touching, and that way you can understand that this is r, this is r, and this a is basically a is equal to 2r, and so this will give you an AR relation in your cubic lattice. But I'm not concerned about the AR relation and packing efficiency in this video, just thinking about the numbers and the distances. Second nearest neighbors. So this is a, this is root 2a, this is root 3a, this again is a, of course. So second nearest neighbor will be along body diagonals, right? Face diagonals, along face diagonals. And what is the number of face diagonals originating from one vertex in a cubic lattice? So that was 12, right? Distance will be root 2a. Fine. Third nearest neighbor, there, this is very easy. You will get along body diagonals. What is the number of body diagonals originating from one vertex in a cubic lattice? 8. Distance root 3a. Fine. Let's think about FCC. I have a separate video about FCC on my channel. You can also go and see that video to see it in a different way, different perspective. But I think this video is more elaborate. I think that is more easier. So because in this video I'm generalizing and talking in terms of directions. Okay, so now what is the closest point from this any point? Now this is one very interesting thing which I would like to talk here. Somebody would say, why are you thinking about this vertex point? Why don't you go and think about this face center point and take distances from here? So let me tell you that from this point also I will get the same kind of directions, because this is a lattice. From here also you see I will get the same arrangement, because this point is not special in a way that you would say that this is at one of the face centers, because if you think about your lattice like this and you extend it, so you can think of the cubes originating from here, and this point being at the vertex, and this point will come at the face center, right? So this just by the basic definition of a lattice, any point on the lattice will have a exactly same neighborhood in all directions. So we can start our discussion analysis from this vertex point. Nearest neighbor, it's along the face diagonal, right? This distance is less than this distance. How much is this distance? So this will be root 2a by 2, right? Half of the face diagonal, and root 2a by 2 is smaller than a, of course, because this is a by root 2, this is a, and root 2 is 1.414 nearly, and this is a by 1. So this has a bigger denominator. Anyway, so then you have these distances also. You'll have to think about how much is this distance, this is a, how much is this distance, this is root 2a, how much is that distance, that is root 3a, okay? How much is this distance? This is one of the V and AFC diagonal, and you can think about that this distance here. You can watch one of the videos which I was talking about on my channel, but here also you can prove it very easily. This distance is A. Let's call this A, B, C. So BC is half of the face diagonal, so that would be A root 2 by 2. Okay, and AB is A. So look at this triangle ABC. Triangle ABC is right angled at B, right? Because the line AB is normal to this whole plane. So that way you can see that this is a right angle triangle, and from here you can do the calculation. This distance, use the Pythagoras theorem, and then your AC, which is hypotenuse of this right angle triangle, would be A root 2 by 2 squared plus A squared. This is basically root 3 by 2 times A. So that distance is root 3 by 2 times A. Okay, this distance is root 2A, this distance is root 3A. So this distance is A, this distance is A by root 2. So you have got the distances. So first nearest neighbor will be along face diagonals, right? And they, because they are along face diagonals, half of the face diagonal, their distance is still only half of the face diagonal, but the number will be the same, because from this point there will originate 12 face diagonals. So in all those directions, at just a length half of the face diagonal, you will get these neighbors, and their distance will be A root 2 by 2. Second nearest neighbor, you will get them along the edges, right? And the number will be 6. So anytime you get along edge, you get this number 6. Anytime you get neighbors along face diagonal, you get this number 12. Distance is A. Third nearest neighbor, and this is where V and A FC lines, V and A FC diagonals become important, because now you will get the third nearest neighbor along V and A FC diagonals, and the number will be extremely large, 24, and the distance will be root 3 by 2 times A. Okay, similarly you can think about the BCC lattice. You see this atom at the body center, and you can think about these distances. This is A, this is root 3A by 2, half of the body diagonal. This distance is root 2A. Okay, this distance is root 3A, and just by a little bit of analysis, you can figure out the smallest, the first nearest neighbor to this point is this point. And since this point is along the body diagonal, in the infinite lattice you will get 8 such neighbors, right, along body diagonals, and the distance will be half of the body diagonal. Second nearest neighbors, this time you will get them along the edges again, and the number would be 6, and the distance would be A. Third nearest neighbor, this time you will get them along body diagonals. No, face diagonals. 12, and distance will be A root 2. This way you can extrapolate, and you can think about fourth or fifth nearest neighbors. These questions are a little bit interesting, thinking about fourth or fifth or sixth and maybe seventh or eighth. There is a very interesting thing which I was thinking about just before I started recording this video, was like, suppose if I go in any random direction from a point in a cubic lattice. Okay, so let me ask you this question in this way. How do I go to the first slide? So what I was thinking about is this is a point here, this is a vertex here. Suppose I go in a random direction, any general direction, and if I keep on moving, will I always hit another vertex if I go in any random direction? What is the probability? And the lattice is infinite. Will I always hit another vertex? This is very interesting. This is like this thing. Suppose you are on Earth and you are looking at the night sky, and you are pointing your finger to some direction in the night sky, and in that direction, what is the probability that you will always hit a star in that direction? There are so many stars. in our universe. Our universe is not infinite, but this question which I am thinking about is about infinite cubic lattice. Might be somebody can see it very easily. I would like to think about it. So thank you very much. I will go think about this thing. Have a nice day.